on about the grade book or grades where they're going to be posted. I haven't updated it yet, but they're going to be posted on my ECC. I don't know what it looks like on your side, but I'll show you. We're not familiar with this. This should be like a gradebook link. Now, for me, it's here. So I need to set it up, but you'll have a gradebook, and you can go in there. That'll be it here. So I'll try to update that today with some grades in there. All right, what we're going to do is we're just going to continue with the nomenclature. The nomenclature is really important. So I want to spend time with it, make sure we're getting it. All right, so let's take a look at number 36. Next. I think we left off talking about acid anions, is that correct? Did we do 36 yet, or not sure? No. Okay. Let's do 36. Write equations for the first and second steps in the ionization, in the step-by-step ionization of selenic acid. And so first we have to figure out what selenic acid is. Selenic acid, what's the anion for selenic acid? Selenate. Yeah. And so selenic acid has the anion selenate. And so we got to figure out what does the selenate anion look like. And so I think about eights. The eights, for example, sulfate. Oh no, because sulfate is right above selenate, periodic table. So sulfate is, what's the formula for sulfate? Is it 3 oxygen or 4 oxygen? 4 oxygen. So selenate is going to be 4 oxygen. And selenate should have the same charge as sulfate, which is 2 minus. And so the acid is going to be, well, we need how many H plus to balance out the charge? 2 of them. So it's going to be H2SeO4. Now, they're talking about the step-by-step ionization. So what that means is it's going to break apart into ions. So the first one that's going to come off is the H plus. For example, we'll talk about this when we get into more chemistry. But if we break off a cation, we're going to be left with an H plus and HSeO4. This is what happens when acids react. When acids react, an H plus comes off. But H2SeO4 has 2 H pluses that can come off in total. And that would leave us with SeO4 2 minus. And so this would be the 2-step, what we call step-by-step ionization, that is creating ions. And how does this occur? Usually this occurs via molecular motion, collisions, these kind of stuff. So that's number 36. Let's go on to number 38. Dihydrogen phosphate ion. Oh, did I talk about dihydrogen phosphate? Monohydrogen phosphate? Yeah? All right. That's right. We had a little bit of confusion there. So we have dihydrogen, monohydrogen phosphate. This is what we call a diprotic acid because it has 2 hydrogens. These hydrogen ions, you know the composition of a hydrogen ion like that, H plus? Well, what's the hydrogen atom consist of? 1 proton, 1 electron. What happens if you lose the electron? Then we're left with a proton. So another name for the H plus ion is proton. So oftentimes this is called the diprotic acid. Phosphoric acid, well, actually let's come up with a formula. Did we already come up with a formula for phosphoric acid? No? Okay. Okay, phosphoric acid. What's the anion? Phosphate. 4 oxygen or 3 oxygen? It's a 3 oxygenate or a 4 oxygen? It's actually a 4 oxygen because the 3 oxygens are just on the outer, L. The inner are all 4. So it's 4 oxygen. The charge? 3 minus. So phosphoric acid, how many H pluses or how many protons are we going to need to balance it out? 3. And so the formula should be H3PO4. We have 3 hydrogen ions attached to the phosphate. Well, the 3 hydrogen ions don't all, when phosphoric acid reacts as an acid, they don't all break off like at the same time. They break off one at a time. And so this is the step-by-step ionization. And so the first hydrogen ion breaks off, and we're going to be left with 2 hydrogens still stuck on there. But each hydrogen's plus, and then phosphate's 3 minus, so this is going to have a net charge of -1. Sorry. -1. Okay, and then what happens is the next hydrogen can break off. The next hydrogen breaks off, we'll just add it to that to keep a running total. Now we'll have 2. And this is going to leave HPO4 with a 2 minus charge. And finally, the last hydrogen can break off, which would be giving us 3 hydrogens and a phosphate. So we've broken this apart into the ions. This is called ionization. Break it apart into the ions. Now, we have an acid here. Acids are neutral. And then we have acid ions. The acid ions have a charge, but like all acids, the cation's the same. What's the cation for acids? The hydrogen ion or the proton. And so this is an acid anion, this is an acid anion. This is not an acid anion because there's no hydrogen here. And so we wouldn't consider this an acid anion. And so we have 2. We can't call this hydrogen phosphate and hydrogen phosphate, so we call this one dihydrogen phosphate. Dihydrogen phosphate. And this one is called monohydrogen phosphate. Just to keep track of them. And so sometimes we'll have some dihydrogen phosphate ion or monohydrogen phosphate ion present as species. Okay, so dihydrogen phosphate ion would be H2PO4 with a 1 minus charge. The hydrogen sulfate ion. So hydrogen sulfate ion is just a hydrogen ion with a sulfate ion, the combination. So we would just have to know the sulfate ion. Sulfate ion is 3 oxygen or 4 oxygen? 4. What's charge?
2 minus.
2 minus. Okay. And so hydrogen sulfate would just be a hydrogen ion and the sulfate ion. It's going to form HSO4 with a 1 minus. There's another name for hydrogen sulfate. You know what it is? Bisulfate. Right. Hydrogen tellurite ion. So tellurite, it's an ite. Hydrogen tellurite. So first we got to figure out what tellurate is. If we can figure out what tellurate is, we can figure out what tellurite is. To figure out what tellurate is, we need to know, is that a 3 oxygen or 4 oxygen? It's going to be a 4 oxygen because of its position. But now we got to figure out the charge.
2 minus.
The 2 minus. So this is, if this is tellurate, what is tellurite? Yeah, it's going to be TO3 charge, 2 minus. And so now they're asking for the hydrogen tellurite. So it's just a hydrogen ion with a tellurite ion. So the formula is going to be HTeO3 with a charge of not 2. Yeah, 1 minus. And So this would be the hydrogen telluride ion. Okay, let's go on to number 40. Let's name these. What's this first one called? This is the hydrogen ion with the carbonate. So we just call it hydrogen carbonate. Another name for hydrogen carbonate is bicarbonate. So this would be bicarbonate or hydrogen carbonate, or baking soda. Baking soda is sodium bicarbonate. What's this one? Actually, this one we just talked about. Do you recognize the anion here? It would be TeO4 with a 2- charge. What's TeO4 with a 2- charge? Tellurite or tellurate? Tellurate. So this would be hydrogen tellurate. This is CO3 with a 2- charge. This is, what's this anion here? This is that sulfate? Well, you look at sulfate. Sulfate is 4 oxygen, so this must be sulfite. And so this is called hydrogen sulfite or bisulfite. Bisulfite's a, I think, you know, in wines, have you ever seen contains sulfites? Sulfite, bisulfite is used to help preserve wine because, you know, they don't want the, you know, did I tell you I went camping in Joshua Tree, and so we went to the dollar store, and I saw, oh, Santa Barbara wine, you know, $1 a bottle, so I bought it. I went back to the campfire, and it tasted like vinegar. It was awful. And what happened was the alcohol in the wine got oxidized by the air. Some air must have gotten in there. Must have been some kind of leak. And so what happens is to prevent the alcohol from becoming oxidized and turning wine into vinegar, they put things like this, bisulfite. Bisulfite's easier to oxidize than alcohol. So if air gets in there, it'll oxidize this. When it oxidizes this, you know, oxygen attacks it, it forms sulfate instead. Kind of stuff. All right, the last section here is the nomenclature of hydrates. Let's talk about hydrates. Hydrates, what are hydrates? First off, you know, and when we look at hydrates, let me show you. Show you something here, probably on the computer. This is the structure of the, would this be like a molecule or a lattice? Yeah. This would be a lattice, but it looks like there are molecules in there. And these aren't actually molecules, although they look kind of like molecules in here. Do you see that? This yellow is a sulfur, and the red are oxygen. And so this is SO4. There are 4 oxygens stuck on it. It has a charge of 2-. So SO4 2- is SO4 2- is sulfate. And so these things here are sulfate ions. These are copper 2 ions. And so this is a lattice of copper 2 sulfate. Does copper 2 sulfate form discrete molecules? No, it doesn't. So what we do is we just take the simplest whole number ratio. The simplest whole number ratio is called the blank formula. Empirical formula, good. And so the simplest whole number ratio would be 1 copper, 1 sulfate. Because this is 2-, this is 2+, they balance each other out. So But if you look at this crystal, do you see there are gaps in the crystal here? There are gaps. In those gaps, we call these like void spaces or whatever, small molecules where ions can fit inside those gaps. One small molecule that likes to wiggle inside these gaps is water. Water molecules. Where do the water molecules come from? Water molecules come from humid air. And so if we have humidity in air, there's water vapor in air. And that water vapor can get trapped in these spaces. There's an attraction because water lights, charges. And so water is very attracted to this type of stuff. Like, so this is a crystal here of copper 2 sulfate. Oh, it's blurry. I don't know why. This is copper 2 sulfate. Actually, this is multiple crystals here. You can see one big crystal here, another one here. They're all kind of intergrown of each other. This is not a single crystal. This is a big single crystal, big single crystal. So we've got some big crystals here of this. But this is called copper 2 sulfate pentahydrate. Copper 2 sulfate pentahydrate because for every copper ion and for every sulfate ion, there's enough space for it to fit 5 water molecules. And so, yeah, that's a lot of water that you can fit in there. And so a lot of water can fit in there. But does it look wet? It doesn't look wet because where the waters are trapped in the crystal structure. You know, it's not like liquid water. These are water molecules stuck in these little caverns in the crystal.
Is the color of the crystal natural or is it dyed?
This is natural. This is natural. However, if you put this stuff in an oven, you're going to dry out the crystal. Because if you put this in the oven, what's going to happen is things are going to start to shape. And pretty soon the water molecules are going to get kicked out of these cavities in the crystal. And so if you heat this up, it'll look like this. I'll show you. We call this the hydrated form. Look at the formula. If you look at the formula here, it's CuSO4.5H2O. So it's solid. And it's called the pentahydrate. Right here. Now, we have another form. It's called anhydrous. You know what anhydrous means? No water. And so let's look at the anhydrous form. Oops, that's the definition of anhydrous. I want anhydrous copper 2 sulfate, so I'll have to switch to that. Maybe a little bit. This is what it looks like. Here they're hydrating the crystals, so this is like totally dried out. And so if you took those big crystals there and totally dried them out, they'd be this color, very light blue, almost white in appearance. And so here they're hydrating the anhydrous. Normally what we see, because our air contains humidity, our air contains water vapor. Since our air contains water vapor, we always see the hydrated form. We don't see the anhydrous form. You can make the anhydrous form, stick it in the oven at 100 degrees or so, and come back a couple hours later, you're going to have the anhydrous form. But if you leave the anhydrous form sitting on the counter, what's going to happen? What's going to happen is it's going to pick up moisture from the air and rehydrate. It's actually, it's pretty easy to do just by cooking it. Here. You can see that, they're cooking it over a burner here, and it's drying out on the edges here. Center still. Okay. Not everything does this. Not everything forms hydrates. many things do. So we have to be aware, are we dealing with the anhydrous salt or are we dealing with the hydrated salt? And so, well, you know, I don't know. So let's take a look at some salts here. 42. It is often possible to change a hydrate into an anhydrous compound by heating it to drive off water. Dehydration. Write an equation that shows the dehydration of potassium fluoride, dihydrate. So potassium fluoride has enough room to fit 2 water molecules per what we call formula unit. That is 1 ion of potassium, 1 ion of fluoride. Well, actually, let's see what the formula is for potassium fluoride. All right. First, let's figure out the formula for potassium fluoride. Potassium, what's the symbol? What's the charge on potassium? Fluoride? And so this is simple. This just balances. It's Kf. Now, it's a dihydrate. And so when we have a dihydrate, that means there's 2 waters for every Kf. So we just tack those on at the end. This is a solid because the waters aren't liquid water. These are water molecules that got captured in there. Crystal structure. And so when we heat this, we can draw an arrow with heat. Heat, the symbol in chemistry for heat is a triangle like this. It means heat. And so if we heat this off hot enough, then those waters will be forced out. And what we'll be left with is this solid Kf, which is the anhydrous, and then 2 waters. These are the waters will be in gaseous or liquid state. We'll put it in the gaseous state because we're driving them. And so this would be the equation that shows the dehydration of potassium fluoride, dihydrate. (44) How many water molecules are associated with one formula unit? Now, a formula unit is an empirical unit. And so formula unit and empirical unit are the same for ionic compounds. However, formula unit can be used for anything, including molecular compounds. Some molecular compounds, we don't have the simplest whole number ratio. So for lattices, we always use the simplest whole number ratio, but for molecules, we don't. We just write the formula for the molecule. And so even though this is a 2-to-2 ratio, we don't simplify this into a 1-to-1 ratio because the molecule of hydrogen peroxide consists of 2 hydrogens and 2 oxygens all bonded together. If we were to simplify this into 1-to-1 ratio, it would be half the molecule. Whereas we automatically do it for lattices. You know, whenever we have a lattice, we get it. So formula unit is just a generic term used for the formula for any kind of compound, whether it's molecular or ionic. Empirical formula is what we use to indicate the simplest. And so the formula unit is CaCl2. That is 1 calcium every 2 chlorines, or 2 chlorides. So how many water molecules are associated? 2. Write the name of this compound. The name of the compound, we would just name this first. What's that? Calcium. Would it be calcium dichloride? No, it's just calcium chloride. We just use the di one, it's all non-metal. This is calcium chloride dihydrate. And so, writing it out, just have calcium chloride. And then dihydrates just tacked on here as an extra word, dihydrate. It's all dihydrate's all one word. The compound barium perchlorate forms a hydrate with 3 water molecules per formula unit. What is the name of the hydrate? What is its formula? Well, let's first write out the formula here. And so barium as fixed charge, I mean, they don't give us a Roman numeral. So barium, what's the symbol for barium? Ba. Now perchlorate, so we got to think, what is chlorate? Is chlorate a 3 oxygen or 4 oxygen? Chlorate's a 3 oxygen, therefore perchlorate will be a 4 oxygen. And what's the charge? Well, barium's charge is easy. What's the charge on barium? 2 plus. What's the charge on chlorate? 1 minus, therefore perchlorate will be the same. So the series all are going to have the same charge, 1 minus. We don't usually write the 1, but we'll write the minus here. And so what's the proper formula for this? How many perchlorates do we need? 2. We need 2 perchlorates. And so we're going to get BaClO4 2. Is that right? Yeah, we need parentheses around ClO4. And so this would be barium perchlorate. So ionic compounds, we don't use a dye or whatever. But even though we don't use the dye here, we got to use it somewhere else. And so we have how many? 3 water molecules? And so what we normally do with hydrates is we'll write a dot here and then write 3 H2O. No, this is very different than normally what we do is we write H2O parentheses with a subscript 3. But for hydrates, we write in front like this. For other things, to indicate we have multiple units, we write it as a subscript here. Parentheses, subscript. We don't do it here. So what do you name this? We would name this barium perchlorate. What? Trihydrates. So hydrates aren't that tricky to name or to write the formulas for. Let's just look at some general problems now. So we went through all the sections in the chapter. And so just for general practice, we have some. I expect you to know what chromate is. You know, I wouldn't give it to you. You should know chromate. You should also know dichromate. They're giving it to you here. But let's write. Well, we could just say the formulas quickly. Barium nitrite. Barium is Ba2 plus. Nitrite. Well, what's its nitrate? Is nitrate a 3 oxygen or 4 oxygen? 3 oxygen in charge on nitrate? Minus 1. And therefore nitrite would be NO2 minus. And so barium nitrite NO2 minus. We need 2 of them, so it's just going to be Ba parentheses NO2 2. That'd be the barium nitrite. Sodium hydrogen carbonate. So this is also known as sodium bicarbonate or baking soda. So what is the formula? Well, sodium ions should be pretty straightforward. Sodium is Na with the charge of 1. Yeah. Now, what is hydrogen carbonate? Well, it's carbonate. What is carbonate? A 3 oxygen or 4 oxygen? 3 oxygen and the charge? 2 minus. So carbonate is that. And so we need to add a hydrogen ion, and we're going to make HCO3 with a charge of 4 minus. And so while that balances, we end up with NaHCO3. Sodium hydrogen carbonate or sodium bicarbonate. Aluminum nitrate. So if we look at nitrate is a 3 oxygen we said with a charge of minus. Aluminum is what charge? 3 plus. And so we're going to need how many nitrates? 3. Nitrate's a very common ion, a very important ion. So this one, aluminum nitrate, will be AlNO3, 3. What's next? Calcium chromate. Right, you have to imagine that, you're going to have to memorize chromate. Now, chromate's not on the periodic table. And so you'll just have to memorize it's going to be a 4 oxygen with 2 minus charge. 0, 4, 2 minus. For these types of things, we don't have the pattern in the periodic table. So for these types of things, the way I memorized chromate, well, the way I memorized it was I wrote it down. I just sat down and wrote, on a sheet of paper. I just kept writing it. I don't know how many times, 50, 100, 150 times I wrote it. And then what that did was it got it into my motor memory. And so when I hit chromate again, I just wrote it down. I didn't really think about it. I just wrote it down. It's weird. It's like driving a car. Sometimes you don't realize, how did you get there? You didn't really think. And so it's one of those types of things. If we can get it to that level, that'll be good. But anyway, this is chromate, and we have calcium. So calcium is what charge? 2 plus. So putting these together, they're balanced. So it's CaCrO4. That would be calcium chromate. Chromium, those chromates and dichromates are used in a lot of processes, and even in concrete. Sometimes they call chromium and chromate chromium 6. Have you ever heard of chromium 6? Chromium 6. There's some kind of water contamination. There's a movie made about it. I didn't actually see the movie, and I'm not that familiar with the story, but did you hear about it? Some huge environmental thing where the water was contaminated with chromium 6. But it's not chromium 6 plus. It's chromium, yes, in a way it's chromium 6 plus. What is the charge on chromium in chromate? If these are 4 oxides, then chromium is what charge? And so this will just be a little side topic here. Sometimes they call chromate chromium 6 because if those are 4 oxides, what is the charge on chromium? This is minus 8. This has got to be, you're right, it's got to be plus 6. It's got to be plus 6 because minus 8 plus 6 gives us minus 2. And the whole thing is minus 2. That's what the charge on the ion is. And therefore this is called chromium 6 because it has a 6. But usually when we're talking about chromium 6, we'll use the Roman numerals like this, not this. So this is why sometimes I write the Roman numerals. This. But, let's see.
Question. Why isn't that part of the variable charges?
Why isn't? Can you repeat?
Why isn't chromium 6 part of the variable charges listed?
Chromium, why isn't it one of the charges? Okay, because there's a distinction. The distinction is that chromium 6 cannot exist by itself, whereas chromium 2 and chromium 3 can exist by itself. chromium-6 has to be bonded to oxygens. Like, I mean, remember I showed you that the shot of sulfate, how the sulfur is bonded to the oxygens? Chromium does the same thing. So the only way you can get chromium in this +6 is to bond it to something and form. Here, I'll show you what let me just show you what it looks like. And hence, this is why I have the distinction. The distinction with the Roman numeral is when we have a Roman numeral like that, it's not the free ion, because the free ion, what we call the free ion, cannot exist by itself. Sure, we can get chromium in the +6, but it has to be linked to these oxygens. Otherwise, it's way too unstable. This is dichromate. Dichromate links via one bridging oxygen like this, chromium, oxygen, chromium. It doesn't like to link with two oxygens. So for example, if we had chromium, oxygen, oxygen, chromium, then it would be Cr2O8, which would be just two chromates, right? But one of the oxygens leaves. The reason is an oxygen-oxygen bond like that, is what we call a peroxide. Peroxide are unstable links. So what happens if one of these oxygens goes, and form this, is Cr2O7. One of the oxygens is gone. But anyway, this is dichromate over here. This is chromate. Dichromate, what's the charge? You know, if we look at dichromate, what is the charge on chromium in dichromate? Well, what is the formula for dichromate? Dichromate dichromate should be two chromates. If you take two chromates, it would be Cr2O8. Right? Cr2O8, but it's not because we have to drop one of the oxygens, so it's actually Cr2O7, 2 minus. The oxygens is wrong. And so if we look at dichromate, then we have 7 oxides. 1, 2, 3, 4, 5, 6, 7 oxides and 2 chromium. The 2 chromiums are going to be what charge? Well, 7 oxides is 7 times minus 2 is minus 14. This whole thing has to give a net -2 charge right here. And so the positive charge must be positive 12. Positive 12 minus 14 gives us minus 2, which means each chromium is what charge? +6. Okay, so now the distinction. Usually if I have chromium 2 plus, no problem. If I have chromium 3 plus, no problem. But if I have chromium 6 plus, big problem. Chromium 6 plus is not happy. And so this is not one of the ions you memorize because it's terribly unhappy. It's not going to exist by itself. And the only way it exists is because it's inside here. If it's inside here, we call it chromium with the Roman numeral 6. Now, does it make sense that we have chromium 6? What about chromium 7? Is chromium 7 possible, which would be even less happy? Well, do you see this one? We say that the chromium in the 6 plus. Now, we don't say charge in this case. We call it the oxidation state is 6 plus. That could have dual meaning. It could be the charge, or it could just be this kind of Roman numeral type deal where it's stabilized by the oxygens here. Now, let me show you something about this. How about chromium +7? So chromium can have variable charges. So for example, it could have +2. There's a reason for that. It could have +3. So if it's +2, it's like titanium. If it's +3, it's like scandium. It can have more charges though. Did you know chromium can have like +4, +5, if we're at +5, it's like this. If we go to +6, chromium's 24 electrons. If we go to +6, we're at 18 electrons, which is like argon. Would it go to +7? Would chromium go to +7? No, because we go past 18. And so chromium won't. Will vanadium go +6? Vanadium won't go +6. What's the max vanadium will go? +5. What's the max titanium will go? What's the max scandium will go? +3. And then let's go the other way. Manganese +7. Look at the numbers here. Do you see the numbers? 7B. The max iron will go, these are going to be 8, basically. Max, these will go 1, 2. Do you see those numbers there? So those will help you, potentially. But. And so we call that the maximum oxidation state, chromium-6. Now, Chromium-6 was what's her name? Oh, that's right, Aaron Brockovich. You heard of Aaron Brockovich? A movie was made. Long time ago. Chromium-6. I'm sorry?
Maybe if you type his name.
Oh, yeah, that's true. Oh, here it is. What is chromium-6 and how did it infiltrate America's drinking water? Chromium-6, the cancer-causing agent and chemical best known for its role in Aaron Brockovich's story, has been found at higher than recommended levels in tap water, supplying 2/3 of all Americans. Wow. I don't know. I don't know. Oh, the source of this is science. Wow. Science is a very respectable source. The real life unhappy ending. Well, anyway. If you're interested, you can read more about it. Well, anyway, yeah, chromium-6 is used in lots of different stuff for different things. But let's continue on with practice. So we did calcium chromate. Let's go on to 51. Aluminum bromide. And so the first thing, when we look at bromide, we think bromate. Bromide, bromate. So bromate is what? Bromate, what's the formula for bromate? BrO3 charge -1. It's bromate. So bromide must be in charge. Yeah. So that's bromide. Aluminum bromide. We have aluminum, which is 3+. So we'll need 3 bromides. Take care of that. So this will just be AlBrO2 3. Aluminum bromide. Potassium dichromate. Potassium dichromate is a very common chemical. You know, actually, when we think about it, there are many. You know, I'm thinking like every single restaurant now in America has a sign that says, you know, well, not in America, in California, it has a Proposition 65 warning, you know, that some ingredients may or have been known to cause. You know, pretty soon it loses its effectiveness, you know, warning. The Proposition 65 warning at the gas pump, you know, and so many of them, you don't know, you know, what's truly going to be a significant risk or what's not. So it's starting to lose its meaning. It's like water, you know. Everybody knows water is toxic, right? You can drown. But, you know, people don't put up warning signs. Or do people put up warning signs? Did I put up that warning sign for the swimming pool? The swimming pool says, warning, you know, swimming pool contains hydrogen. Did you see that? Yeah, it's kind of a joke, but yeah. Obviously, it contains lots of hydrogen, right? Lots of H2. So it could be potentially, you know, quite dangerous. But yeah, so it's our job to figure out, you know, what exactly the risk is. Let's continue here with potassium dichromate. Potassium dichromate is risky stuff. Potassium dichromate is, well, what was the formula? Did you know chromate? Chromate is CrO4 minus, right? And so what is dichromate? Cr2O7. What happened to that oxygen? Yeah, because of the bond. And the charge is 2 minus because of the way they're linked together. They maintain, it doesn't go 4 minus. You'd think it'd go 4 minus, but it doesn't because of how they link together. And so Cr2O7, 2 minus. Potassium is K plus. And so potassium dichromate is K2Cr2O7. Potassium dichromate. It's used in leather tanning a lot. Barium dihydrogen phosphate. Barium dihydrogen phosphate. Well, barium seems to be a popular ion. Here, Ba. What's the charge on barium? Ba2 plus. Sulfite, or actually no, not there. Barium dihydrogen phosphate. So what is dihydrogen phosphate? I know what phosphate is. Phosphate is 4 oxygen or 3 charge. So dihydrogen means we have 2 hydrogens. So it's going to be H2PO4 charge. 1 minus. And so it looks like we're going to need 2 of these. Balance out the charge. It's going to be BaH2PO4 2. Barium dihydrogen phosphate. Rubidium selenate. Selenium is right below sulfur, so we know what sulfate is. Selenate would be selenate. Rubidium is Rb charge plus, so this is Rb2SeO4. Here, we don't need parentheses around rubidium. Say the same thing. 53. Cobalt-2 hydroxide. So finally we have a variable charge. Cobalt likes to form +2 and +3. But, you know, there are other charges available to cobalt as well. But those are usually found when it's bonded to other things. And so cobalt +3 is quite reactive. Cobalt-2 just means it's cobalt with a 2+ charge. Hydroxide. Hydroxide is one of those ones you just have to memorize. Hydroxide is OOH or OH charge? -1. So we'll need 2 of those. The cobalt-2 hydroxide is COOH2, lowercase l. All right, let's take it. No, it's not quite yet. Let's finish this one here. Zinc chloride. Zinc, is that variable charge or fixed charge? here, is it variable charge or fixed charge? It's fixed. Well, how do you know you memorized it? It's fixed charge. How do you also know is did they give a Roman numeral? They didn't give a Roman numeral, so this is fixed charge. This is variable charge, this is variable charge, variable charge. So we have one fixed charge in this series, that's zinc. The charge on zinc is 2 plus. Then we have chloride. Chloride is Cl minus, so this is just ZnCl2, zinc chloride. A lead is a variable charge. It can be lead 2 plus, Pb, chromium, lead 2 plus, or lead. What's the other charge on lead? What group is lead in? What group is lead in? 14. The other charge on lead is 4. So it's lead 2, 4. What's the charge on tin? 2, 4. Like carbon, you know, carbon could be 2 in carbon monoxide, or it could be 4 in carbon dioxide. Well, anyway, this is lead 2 nitrate. What's the formula for nitrate? Is it 3 or 4? 3 or 4 oxygen? 3. And then charge? -1. So we have 2 of those to balance this out. So lead 2 nitrate would have this formula, PbNO3 2. Copper 1 nitrate. Copper can form a charge of 1 and 2. You know, copper is right above silver. Silver is only 1 charge on silver. Copper can have 2 charges. You know, this is group 1B or group 11. +1 and +2. 2 charges on copper. So this is copper with a +1 charge. And then we have it bonded to nitrate, which we saw earlier, NO3 minus. So this is just CuNO3. That would be copper 1 nitrate here. Oh, let's do this one, and we'll take a break. 56 PbS. Okay, Pb is lead. Is lead variable or fixed charge? Yeah, it's variable. And so we have to use a Roman numeral for this. Sulfur or sulfide would be fixed charge. What's the charge on sulfide? 2 minus. And so that means lead must be 2 plus, and therefore it is going to be lead 2 sulfide. Lead Roman numeral 2 in parentheses sulfide. What's the charge on this? OH is hydroxide, it's minus. Therefore silver is plus. Is silver variable charge or fixed charge? Fixed. And so that would just be silver hydroxide. Silver hydroxide. Cobalt, fixed charge or variable charge? Variable. And so we need Roman numerals. Bromide is fixed at -1, so it's -1, -2, -3. Therefore cobalt must be +3. So this would be cobalt, Roman numeral 3, bromide. All right, we'll take a break here and then we'll